So in the first of these videos on thermodynamics, we're going to introduce the term lattice enthalpy. Lattice enthalpy is an important term and it is the basis of the whole of this pack 1. So we're going to have a look at this term lattice enthalpy. You might remember using the term lattice in the first year during structure and bonding. So let's just remind ourselves where we came across the term lattice. So when a metal and a non-metal react, they're going to form ionic compounds. So when sodium and chlorine react, we form sodium chloride. And when we form something like sodium chloride, we can remember from our earlier studies, even in GCSE, that we form sodium chloride in a regular pattern of oppositely charged ions, and we call that a giant ionic lattice. And giant ionic lattices are held together by ionic bonds. So an ionic bond is the electrostatic force of attraction between oppositely charged ions in the lattice. So what is holding the lattice together? The strength of bonding in a lattice is given by its lattice enthalpy. So lattice enthalpy is going to tell us the strength of the ionic bonds. So there are two definitions that we are going to need to come across and learn. The first one is about dissociation, and that means breaking. And the second one is about forming, which means making. So we've got the enthalpy required to break the lattice and the enthalpy required to make the lattice. These two numbers are interlinked and we're going to talk about how later. So break or form. The first one we're going to consider is the dissociation one. The enthalpy of lattice dissociation. So the enthalpy of lattice dissociation is the enthalpy change, and what's important in this definition is which words are the most important to separate, that's the breaking, 1 mole of solid ionic compound. So important in this pack that you know what the 1 mole is of, and in this case it's solid ionic compound. So 1 mole of solid ionic compound. And what are we going to break it into? So we need to know what to turn it into. We're going to turn it into gaseous ions. So what I want you to do is I want you to pause this video and I want you to try to write an equation that will represent this definition for sodium chloride. So if we read it as if it was sodium chloride, it would be the enthalpy of lattice dissociation is the enthalpy change to separate 1 mole of solid sodium chloride into its gaseous ions. So pause the video and see if you can come up with that equation. So this is what you should have got. I started on the left with 1 mole of sodium chloride as a solid, put my state symbols in, very important. And on the right I have got sodium ions and chloride ions, because that's the ions of sodium chloride, and they're gaseous. I've got state symbols. State symbols are essential here. So let's think about these. It says enthalpies of lattice dissociation are always as bonds are being broken. Always what? So we're looking for either the word positive or negative. Does it take energy to break that lattice up, or is energy released when that lattice is broken up? And what we know is that in order to pull apart those ions, we're going to need some energy. So we're going to have to put in energy. Imagine just pulling apart two things that are attracted, so two magnets that are attracted. You have to put energy in. And so those energy changes are positive. And in chemistry, a positive energy change is called an endothermic energy change. So I want you to, again, to think about what that means. So enthalpy of lattice dissociation is a measure of the strength of the electrostatic attraction between the ions. So it is a measure of the strength of the ionic bond. The bigger, more positive the number, the stronger the ionic bonds will be. So pause the video and have a go at this little question. Choose out of these two which one you think has got stronger ionic bonds. So I think it's sodium chloride because 771 is a bigger number than 705. The enthalpy of lattice dissociation is more positive, so more energy is needed to overcome the electrostatic forces of attraction between the oppositely charged ions. Therefore the bonds must be stronger. More energy is needed. So the second of these two definitions is called the enthalpy of lattice formation. We're now looking at making it So what are the key terms? So it's when 1 mole of the solid ionic compound formed from its gaseous ions. So pause the video again, have another go. Can you write this equation forming 1 mole of magnesium bromide from its gaseous ions? So I've had a go. I formed 1 mole of solid magnesium bromide on the right here from its gaseous ions. So magnesium ions, magnesium in group 2, 2 plus, and bromide ions, Br minus, 2 bromide ions in magnesium bromide, and they're both gaseous because that's what the definition said. And here, when we're forming, when ions come together, there's a release of energy as the attractions form, and so these are going to always be negative. And the word for a negative energy change in chemistry is exothermic. So again, it's a measure of the strength of the ionic bond. What we can say about the two processes is the value for dissociation and formation of the same compound will be the same size. So if you want to use the mathematical term magnitude, you could, same size, but have the opposite sign. So we've got 771 plus for the dissociation of sodium chloride. If we looked at the formation, it would be minus 771. Same value, but different opposite signs. So pause the video one more time and see if you can answer the question at the bottom of the page. So there we go. I have reversed the process because that was formation and I wanted dissociation, so it's the other way around. And I've changed the sign from minus 742 to plus 742. So that's the end of the first little video where we're introducing the term lattice enthalpy. The whole pack now is going to be about looking at how we could calculate this lattice enthalpy value to give us a measure of the strength of ionic bonds by using a series of other changes that we can measure. So we're going to look at a whole series of enthalpy changes, and we're going to look at how we would put those then together to form a cycle that we could use Hess's law on. So this whole pack is now going to be about how we could calculate lattice enthalpy.